Hello, I'm Tseh, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Femtochemistry, an examination of atomic resolution in chemical reactions. The 1996 Nobel Prize in Chemistry recognized the groundbreaking work of Dudley, Robert Herschbach, Yuan and John Charles Polanyi in the field of femtochemistry. The collective body of research presented by these scientists, focusing on chemical reactions observed with atomic resolution, revolutionized the understanding of molecular dynamics. This essay undertakes a comprehensive evaluation of their claims, methodology, and resulting interpretations, examining the core assertions presented across their publications. We will traverse the landscape they created, scrutinizing the evidence they provided and assessing the lasting impact of their insights on the scientific community. Section 1: Initial explorations of molecular beam scattering. Early contributions from Herschbach and Lee centered on the development and application of molecular beam scattering techniques. A primary claim in this early phase involved the ability to precisely control the kinetic energy and internal states of reactant molecules within intersecting molecular beams. This control, they argued, allowed for a detailed mapping of the potential energy surfaces governing chemical reactions. Their experiments, particularly on alkali halide reactions, provided significant evidence supporting this claim. They demonstrated that the angular and velocity distributions of product molecules could be directly related to the shape of the potential energy surface, offering insights previously unobtainable. This approach presumed a well-defined interaction volume at the intersection of the beams and sufficiently low pressures to ensure collision events were primarily bimolecular. The validity of this presumption rested heavily on the careful design of the apparatus and the precise control of beam parameters. Later reinterpretations of some of these scattering data, incorporating more sophisticated theoretical models, have somewhat nuanced the initial interpretations, revealing the complexity inherent in extracting detailed potential energy surfaces from scattering experiments alone. They revealed, for example, that interactions within the detected product beams, after initial collision, could impact the measurements obtained, complicating analysis. Section 2: Infrared chemiluminescence and energy disposal in reactions. John Polanyi's work focused on the dynamics of chemical reactions through the analysis of infrared chemiluminescence emitted by product molecules. A central assertion was that the vibrational and rotational energy distributions of nascent product molecules directly reflected the energy release dynamics of the reaction. By measuring the infrared emission spectra of these products, Polanyi and his colleagues inferred the partitioning of energy among different degrees of freedom. They claimed that reactions exhibiting inverted vibrational populations, where higher vibrational levels were more populated than lower levels, indicated a predominantly attractive potential energy surface, where energy was released primarily as the reactants approached each other. Conversely, repulsive surfaces led to greater translational energy of the products. The strength of this methodology lies in its ability to probe the immediate aftermath of a chemical reaction, providing information on energy disposal before secondary collisions could occur. However, the interpretation of the chemiluminescence spectra relies on accurate knowledge of Einstein coefficients for spontaneous emission, and uncertainties in these values could influence the derived energy distributions. A further limitation arises from the fact that only vibrationally excited molecules emit infrared radiation. Information concerning vibrationally cold products requires alternative techniques. Section 3: The advent of femtosecond lasers and real-time observation. The development of femtosecond lasers provided the impetus for the field of femtochemistry, enabling the direct observation of chemical reactions in real time. Amid Zuil's pioneering work, heavily influenced by the earlier findings of Herschbach, Lee, and Polanyi, is inseparable from their foundation. This development allowed Zuil to be honored in a subsequent decision, an honor fundamentally linked to the base research A crucial claim was that femtosecond laser pulses were sufficiently short to freeze the motion of atoms during a chemical reaction, allowing for the acquisition of snapshots of the transition state by using a pump probe technique where a first laser pulse initiated the reaction and a second pulse probed the evolving system. It became possible to monitor the formation and breaking of chemical bonds with unprecedented temporal resolution. Initial experiments focused on simple bond fission reactions, such as the dissociation of iodine cyanide, iodine molecule, and sodium iodide. The observation of oscillatory behavior in the transient absorption spectra provided compelling evidence for the existence of vibrational coherence in the transition state. This coherence reflected the synchronized motion of atoms along the reaction coordinate. The interpretation of these experiments is not without its challenges. The observed signals are often complex, involving contributions from multiple electronic states and vibrational levels. Furthermore, the interaction of the intense laser pulses with the molecules can itself influence the reaction dynamics, a phenomenon known as laser-induced dynamics. Accurately disentangling these effects requires sophisticated theoretical modeling and careful experimental design. Section 4, Unraveling the Dynamics of Unimolecular Reactions. Femtochemistry has provided valuable insights into the dynamics of unimolecular reactions, where a single molecule undergoes isomerization or dissociation. A key argument within this research area is that the rate of unimolecular reactions does not always follow the predictions of statistical theories, such as RRKM theory, Rice-Ramsburger-Castle-Marcus theory. Statistical theories assume that energy randomization within the molecule is faster than the rate of reaction, leading to a statistical distribution of energy among the various vibrational modes. However, femtosecond experiments have revealed instances where energy randomization is incomplete, leading to non-statistical reaction dynamics. Consider the isomerization of stilbene, where the molecule twists around a double bond. Femtosecond studies have shown that the rate of isomerization depends on the initial excitation energy and the specific vibrational modes that are excited. This suggests that energy flows preferentially along certain pathways rather than being randomized throughout the molecule. These observations challenge the fundamental assumptions of statistical theories and highlight the importance of vibrational energy redistribution in determining the rates and pathways of unimolecular reactions. Section 5, Exploring Bimolecular Reactions with Femtosecond Resolution. While femtochemistry initially focused on unimolecular reactions, its application to bimolecular reactions has yielded significant information about the transition state region. A prevailing assertion is that femtosecond experiments can provide a direct view of the fleeting interactions that occur as reactants approach each other and form products. One example is the study of the reaction between hydroxyl radical and carbon monoxide, which is a crucial step in combustion processes. Femtosecond experiments have revealed the formation of a transient complex, HOCO, which exists for a very short time before either dissociating back to reactants or forming products. The lifetime of this complex and the pathways leading to different product channels depend on the collision energy and relative orientation of the reactants. These experiments demonstrate the power of femtochemistry in elucidating the detailed mechanisms of bimolecular reactions, providing insights that are difficult to obtain from other experimental techniques. Section 6, Control of Chemical Reactions with Coherent Light. A particularly ambitious goal of femtochemistry is the control of chemical reactions using shaped femtosecond laser pulses. The promise is that by tailoring the temporal and spectral characteristics of the laser pulses, it is possible to selectively excite specific vibrational modes or electronic states in a molecule, thereby steering the reaction towards a desired product. This concept, often referred to as coherent control, has been demonstrated in a variety of systems. For instance, by using a pulse shaping technique, it has been possible to selectively cleave different bonds in a molecule or to favor the formation of one isomer over another. The implementation of coherent control relies on a detailed understanding of the interaction between light and matter and the ability to predict how different laser pulse shapes will influence the reaction dynamics, while the potential applications of coherent control are enormous, ranging from drug synthesis to materials science. Significant challenges remain in translating these concepts to more complex systems. Section 7 Femtochemistry and condensed phase reactions. Extending femtochemistry to condensed phase reactions presents several challenges, including the presence of solvent molecules and the rapid dissipation of energy. Researchers assert that femtoscond techniques can still provide valuable insights into the dynamics of chemical reactions in solution. Despite the increased complexity, experiments have demonstrated that the solvent can significantly influence the reaction rate and pathway, and that energy transfer from the reacting molecule to the solvent can occur on a timescale of picoseconds or even femtosconds. Studies of photoisomerization reactions in solution have shown that the solvent can cage the molecule, preventing it from isomerizing, or that it can facilitate isomerization by providing a pathway for energy dissipation. These experiments underscore the importance of considering the role of the solvent in understanding chemical reactions in condensed phase. Section 8 Theoretical advancements in femtochemistry. The interpretation of femtoscond experiments relies heavily on theoretical simulations. Several theoretical approaches have been developed to model the dynamics of chemical reactions at a femtoscond timescale, including molecular dynamics simulations, quantum mechanical calculations, and mixed quantum classical methods. A key claim within this research area is that accurate theoretical simulations can provide a detailed understanding of the reaction mechanism and can help to interpret the experimental observations. Molecular dynamics simulations, for example, can be used to simulate the motion of atoms and molecules during a chemical reaction, providing insights into the pathways that are followed and the energy flow that occurs. Quantum mechanical calculations can be used to calculate the potential energy surfaces that govern the reaction dynamics, and mixed quantum classical methods can be used to treat the electronic and nuclear degrees of freedom at different levels of accuracy. The accuracy of these simulations depends on the quality of the potential energy surfaces and the approximations that are used to solve the equations of motion. Section 9 Femtochemistry and biological systems. The application of femtochemistry to biological systems is opening up exciting new avenues for understanding the fundamental processes of life. Scientists argue that femtoscond techniques can be used to study the dynamics of protein folding, enzyme catalysis, and photosynthesis, among other processes. For example, femtoscond experiments have revealed the intricate steps involved in the initial events of photosynthesis, where light energy is captured by chlorophyll molecules and transferred to other molecules in the photosynthetic reaction center. These experiments have shown that energy transfer occurs on a timescale of femtosconds to picoseconds, and that the efficiency of energy transfer is highly dependent on the structure of the photosynthetic complex. Similarly, femtoscond experiments have provided insights into the dynamics of protein folding, revealing how proteins rapidly fold into their native structures. These studies demonstrate the potential of femtochemistry to unravel the complex dynamics of biological systems. Section 10 Persistent challenges and future directions. While femtochemistry has revolutionized the understanding of chemical reactions, several challenges remain. One challenge is the complexity of interpreting the experimental data, which often involves contributions from multiple electronic states and vibrational levels. Another challenge is the development of accurate theoretical models that can accurately simulate the dynamics of chemical reactions, particularly in complex systems. A continuing challenge is the extension of femtochemistry to more complex systems, such as liquids and solids, where the presence of solvent molecules or other environmental factors can significantly influence the reaction dynamics. Future research directions include the development of new experimental techniques with higher temporal and spatial resolution, the development of more sophisticated theoretical models, and the application of femtochemistry to a wider range of chemical and biological systems. The pursuit of these goals will continue to push the boundaries of our knowledge and understanding of the fundamental processes of chemistry and biology. Conclusion: the collective body of work from Herschbach, Lee, and Polanyi provided invaluable contributions to our understanding of the atomic and molecular dynamics, paving the way for the era of femtochemistry. Their meticulous experimentation and insightful interpretations remain testaments to the power of combining innovative experimental techniques with rigorous theoretical analysis. They established the foundations upon which later scientists could build, allowing for real-time observation of the chemical process. The initial presumptions and analyses, while subject to the scrutiny of time and later discoveries, stand as benchmarks against which subsequent findings are compared. The legacy of this work extends far beyond the specific reactions studied, impacting diverse fields ranging from materials science to biology. Although nuances and reinterpretations have emerged, the core claims regarding the relationship between energy disposal, potential energy surfaces, and reaction dynamics remain profoundly influential, securing their place as pioneers in the field of chemical kinetics. The future of femtochemistry appears exceptionally vibrant, promising further revelations about the intricate dance of atoms and molecules that underpins the world around us.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.